Okay, hello. We are going to be recording today 7.1, Day 1, Exponential Growth and Decay. We're going to start this new unit. So, we're starting off with looking at, make sure you guys can see this, and a exponential function. So where the independent variable is an exponent. Has the form of f of x equals a times b to the x, where a, of course, cannot be 0, and b is a constant. B has to be greater, when b is greater than 0, the function is called a growth function, because over time it grows and gets bigger. And this occurs when the initial amount increases by the same percent over a given period of time. So, basic example of a growth function. Easiest one to graph is f of x equals 2 to the x power. And the way we graph a growth function is we make a table, or a t-chart, whatever you want to call it. All right, so we're going to pick some random x values. The ones right around 0 are the easiest one to graph. We're going to start with 2 to the 0 power. 2 to the 0 power is 1 because everything to the 0 power is 1. 2 to the first power is 2 because anything to the first power is itself. 2 to the second power, 2 squared is 4, and 2 to the third power, 2 cubed is 8. Going back to the negatives, remember when we have a negative exponent, we switch the numerator and denominator and get rid of the negative. So this is 1 over 2 to the first, so 1/2. 2 to the negative 2 is 1 over 2 squared, so that's 1 over 4. And 2 to the negative 3 is 1 over 8. So now we will graph those points. So negative 3 and 1/8. Negative 2, 1/4. Negative 1, 1/2. 0, 1. 1, 2. 2, 4. And 3, 8. And so our graph is going to look like this. All right, so if you look at this graph, you'll notice some things about it. First off, there's no limit to the domain, so that's all numbers, all real numbers, negative infinity to positive infinity. The range, that graph is not going to go below 0, so it won't ever touch 0 either. It's going to get really, really close, but it goes up to infinity. The y-intercept is at where the x value is 0, so that's 0, 1. The asymptote, notice there is a horizontal asymptote at y equals 0. Now, in behavior, as x goes to the left towards negative infinity, f of x is getting closer and closer to 0. As x goes to the right towards positive infinity, f of x is getting closer and closer to infinity. So, again, as those x values decrease, the graph of the function is getting closer and closer to the x-axis. The function never reaches the x-axis because the value of 2 to the x cannot be 0. There's no power that I can raise 2 to make it equal 0. So the x-axis is an asymptote. And that an asymptote is a line that is a graphed function approaches as the x gets very large or very small. All right, example 2. We're asked to graph the exponential growth by graphing the parent graph of f of x equals 3 to the x. So first off, we're going to graph 3 to the x, and again, we're going to make an xy chart. So this, we'll just do negative 2, negative 1, 0, 1, and 2. Again, negative 2 is 1 over 3 squared, so that's 1 over 9. Negative 1 is 1 over 3. 0 is 1, because anything to the 0 power is 1. 3 to the first is 3. 3 squared is 9. Okay, so we can graph our parent function. So negative 2, 1/9. Really close to 0, but not quite there. Negative 1, 1/3. 0, 1, 1, 3, and 2, 9. So our parent function looks like this. Okay. So now we're going to transform. Now the transformations are the same as we've had all year. We have A, we have H, and we have K. Our A in this case is negative 1/2. That negative means that we're going to reflect in the x-axis, and the 1/2 means we are going to compress it vertically. The H is negative 4, and so that's going to translate 4 units left. And the K is 1, so that means we translate up 1 unit. Okay, now we are going to apply some transformations. So the first transformation we're going to apply is the negative 1/2. So what we're going to do is we're going to take the same x values, negative 2, negative 1, 0, 1, and 2. But now we are going to multiply the 1/9, the 1/3, the 1, the 3, and the 9 by negative 1/2. So negative 1/2 of 1 over 9 is negative 1 over 18. Negative 1/2 of 1 over 3 is negative 1 over 6. Negative 1/2 times 1 is negative 1/2. Negative 1/2 times 3 is negative 3/2. And negative 1/2 times 9 is negative 9/2. So now we're going to plot these points, negative 2, negative 1/18, so really close to 0. But on the negative side now, negative 1, negative 1/6, still really close to 0. 0, negative 1/2, still really close to 0. 1, negative 3/2, same thing as negative 1/2. And 2, negative 9/2, so that's the same thing as negative 4/2. So like that. So our graph now, after the reflection and the compression, it's going to look something like that. Okay, so you can see that things are closer to the x-axis, and it's reflected, but still has that hockey stick shape to it. Now, we're going to move everything to the left 4 and up 1. So all of those points that I just plotted, I'm going to move 4 units to the left and up 1. So 1, 2, 3, 4, and up 1 goes there. I'm going to change color so that we can see the difference here. So do that again. 1, 2, 3, 4, up 1. 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 And then 1, 2, 3, 4, up 1. Okay, so now it looks like that. And that red line is our final graph, that negative 1/2, 3 to the x plus 4 plus 1. Okay. So next we are asked to identify the value of k and write a function for the graph h of x equals f of x plus k as it relates to f of x equals 3.5 to the x. Well, f of x is 3.5 to the x. The k value, in this case, is also our horizontal asymptote. So keep in mind, it's a very important fact, our k is equal to our horizontal asymptote. And you notice we have a horizontal asymptote at negative 2. So our k value is negative 2. And because our k value is negative 2, I can rewrite this h of x is equal to 3.5 to the x minus 2. Okay? All right, so exponential growth can be modeled by this simple formula. So a to the t, or a of t, is equal to our initial amount, which is little lower case a, times 1 plus r to the t power. A of t represents the amount after t time periods. Little a is the initial amount, and r is the percent of increase per time. So our growth rate is given by 1 plus r. So I want you to imagine that Mrs. Murray won the lottery. Suppose she takes the lump sum payment. She invests $50 million into an account that yields 5% interest annually. So we're asked to graph the function that models the amount in her account. Now, starting at 50 million, it's going to be growing at 5%, so not a huge growth rate. The growth rate is 1.05, right? So it's going to start off pretty steady, and notice we don't care about any negative time because she won this lump sum payment. It's not like her account's been growing for years. She was a teacher. She didn't have any money. Now she's got $50 million. Okay, so it's going to start off growing slowly, but as time goes on, just like any exponential growth, it is going to increase rapidly eventually. So we can estimate the amount in the account after 20 years by plugging 20 in for t. So a of 20 is equal to our initial amount, which is 50 million, times 1.05 to the 20th power. Okay, so in order to do that, you just type that into your calculator, just like that. 50 million, parentheses, 1.05, close the parentheses, raise it to the 20th power, and press equals. And you'll see that Mrs. Murray now has, after 20 years, not $50 million, but $132,664,885.30. So, interest is your best friend, and time is your best friend in investing, so please start investing today. All right, that's my soapbox. Hope this was helpful for you. If you have any questions, please shoot me an email or a Canvas message, and I'll get back to you as soon as I can. Have a great one.